Center notch film. Object E-8, Lunokhod or Soviet Lunar Rover Vehicle 8, EL number 201. The E-8 space object was designed for transporting a cosmonaut across the lunar surface as part of the N1, L3 complex, and for conducting scientific and technical research on the Moon using a self-propelled vehicle, Lunokhod. Before the first series of E-8 complex launches, several objectives were set. Verifying the possibility of launching the E-8 space object into a translunar trajectory by the UR-500K carrier rocket in conjunction with the correction and braking module, Block DE, upper stage. Testing correction and control systems during the translunar flight and insertion into lunar satellite orbit. Performing braking and descent maneuvers. Testing the soft landing system of the space object on the lunar surface. Verifying the functionality of the self-propelled lunar rover Lunokhod's locomotion system on the Moon. Testing the remote control system, refining radio and television communication systems, and conducting scientific research. The E-8 complex program was carried out in accordance with a resolution of the Central Committee of the Communist Party of the Soviet Union and the Council of Ministers of the USSR, based on the technical specifications provided by the Academy of Sciences of the USSR. The lead organization responsible for the development was the S.A. Lavochkin Design Bureau and Plant, with Chief Designer Gian Babakin. The development of the E-8 rocket and space complex involved teams from design bureaus and scientific research institutes under the leadership of General Designer V.N. Kelemy, Chief Designers N.A. Pilyugin, M.S. Ryazansky, A.M. Isev, V.P. Morichevsky, and S.A. Pashkov, as well as directors of institutes N.S. Litarenko, V.S. Starovoytov, G.I. Petrov, among others. The configuration of the E-8 space object was approved in this form. The E-8 is densely packed with onboard instrumentation. There are around 120 electrotechnical instruments on board, with a total weight of approximately 1,700 kilograms. The structural components weigh 400 kilograms. The propulsion system also weighs around 400 kilograms, with the engine itself weighing 100 kilograms. Overall, the equipment makes up 3/4 of the dry weight of the entire space object. What are these instruments? What are their functions and purposes? What systems are part of the space object? The control and Astro-orientation system is used to manage the position and velocity of the E-8 from the moment it separates from the carrier rocket's third stage until the soft landing on the lunar surface. The Astro-orientation system includes an Astro unit with optical sensors for tracking the Sun and Earth, a monoblock with an electronic logic circuit, and an angular velocity sensor unit. One of the key components of the control system is the stabilization unit, which consists of a gyro-stabilized platform, passive and active stabilization units, altitude and heading control units for lunar landing, engine cutoff automation, apparent velocity control system, and landing control system. The actuators of the stabilization unit during active phases of flight are fixed liquid propellant thrusters. During passive phases, gas microthrusters work alongside the liquid propellant ones. Altitude measurement above the lunar surface is performed by a radar altimeter. The radiotechnical complex provides measurement of the object's flight parameters en route to the moon, reception of radio commands from Earth, and transmission of telemetry, telephotometric data, and television images of the lunar surface. Onboard systems are controlled by pre-programmed sequences and programs generated in flight. The complex includes a transceiver comprising two independent, redundant Earth-to-spacecraft radio links operating in the meter and decimeter bands, and redundant spacecraft-to-Earth links operating in the decimeter band. Telephotometric devices, similar to those used on Lunar 9 and Lunar 13 missions. Television cameras. A preset control block and a programmable timing device. Radio telemetry, formatting, and switching equipment capable of measuring over 800 parameters at a rate of up to 3,200 measurements per second. Four omnidirectional meter band whip antennas serve to receive commands during Translunar Flight and while Lunokhod operates on the lunar surface. Decimeter band antennas are intended for command reception, parameter measurement data transmission, telemetry, TV, and telephotometric signal transmission. The carrier stage KT module antennas provide radio communication during the flight phase. Before descent begins, these are jettisoned together with the external compartments. Antenna switching is managed by the antenna feeder system unit. The antenna feeder unit underwent comprehensive and thorough testing at the factory. Radiation patterns were measured for the low-gain meter and decimeter band antennas, as well as for the high-gain directional antenna. The thermal control system maintains the necessary temperature conditions for onboard equipment operation. Lunar environmental conditions are further complicated by thermal radiation from the moon's surface affecting the Lunokhod. When the sun is at zenith, lunar soil heats up to 185 degrees Celsius. During Lunar Night, the temperature drops to minus 175 degrees Celsius. During the lunar night, the Lunokhod's thermal regime is maintained by a heating unit that uses the isotope polonium-210, which emits thermal energy with a nominal power of 600 watt. The isotope heat source is connected to a hot gas loop. The gas is circulated through the loop by fans. Its flow is regulated by a damper, which is controlled by signals from bimetallic temperature-sensitive elements. During the lunar day, the lid of the equipment compartment opens, allowing heat to radiate into space. When the temperature inside the compartment exceeds the permissible limit, a bimetallic valve activates the water evaporation cooling system. The thermal control system is mounted on a special frame and installed inside the Lunokhod's main body. The isotopic heating unit is located externally. The casing of the heating unit can reach temperatures up to 400 degrees Celsius. Therefore, the Lunokhod is protected from its thermal radiation by a metallic shield. Comprehensive thermal testing of the Lunokhod was conducted in a specially built thermobaric chamber of 600 cubic meters at Lavochkin Mechanical near Sergiev Posad, Zagorsk. Tests were carried out with the standard active thermal control system and multi-layer vacuum insulation. Powerful cryogenic compressors created a vacuum of 5 micromillimeters of mercury within the chamber. Negative temperatures on the chamber's inner screen were generated using liquid nitrogen pumped in by 4 vacuum pumps. Solar thermal flux was simulated using xenon gas discharge lamps, producing a light spot of 20 square meters. The facility also included a lunar thermal radiation simulator. In the thermobaric chamber, the temperature field of the E-8 space object and the thermal operating conditions of its systems were investigated both in flight and during operation on the lunar surface. The purpose of the landing gear was to absorb the kinetic energy of the spacecraft's descent following the shutdown of the low-thrust propulsion stage. Each landing support consisted of a telescopic tube with a damping rod and 2 tubular struts. Upon impact, the damping rod plastically deformed, absorbing the object's kinetic energy. Despite its apparent simplicity, the design required a year of development by a large team and extensive factory bench testing. Shock absorbers were tested under static and dynamic loads across the full range of lunar temperatures. For this, they were placed in special casings with temperature control. Shock absorbers of various designs and materials for the rods were tested. A full-mass model with actual moments of inertia and standard landing gear was dropped from a crane. To simulate lunar gravity, the model was offloaded using rubber dampers to 1/6 of its Earth weight. Drop tests confirmed the calculated data and the possibility of a safe landing. In-factory testing included both static and dynamic evaluations of the spacecraft. Repeated separation tests were conducted for the landing platform or carrier stage, KT module, from the correction and braking stage, D module, and for antenna deployment, as well as for the jettisoning of expendable compartments from the carrier stage KT. These tests confirmed the reliable operation of the separation mechanisms. The self-propelled chassis was designed to transport a payload of approximately 140 kilograms in lunar weight, 800 kilograms on Earth, across the Moon's surface at speeds up to 2 kilometers per hour, with a range of at least 100 kilometers. Several chassis variants were tested. Tracked. Four-wheeled. Eight-wheeled. The tracked chassis risked jamming when turning on loose soil. Its short base increased the chance of tipping on inclines. The four-wheel chassis had a high center of gravity and similarly short base, making it prone to tipping on slopes. The eight-wheeled chassis, with the same overall size, had a longer base and a lower center of gravity. Reliability increased as all 8 wheels were powered. Each wheel hub contained a motor, a 3-stage planetary gearbox, and a mechanism to disengage the wheel from the gearbox. The entire drive system consumed about 300 watts, less than a typical household iron. To assess the traction properties of lunar soil, a traversability assessment device, PROP, was installed. A ninth, freely rotating wheel measured the distance traveled. All chassis variants were developed manufactured and tested at the All-Union Scientific Research Institute of Transportation Engineering, NE-Transmash. Tests were conducted on lunar soil simulants and simulated lunar terrain. The self-propelled chassis was also tested on inclined planes. Extensive testing demonstrated the high reliability of the 8-wheeled chassis. Locomotion testing continued at the Lavochkin plant. A special lunar terrain simulator, Lunokhod-0, was built, replicating lunar surface features and equipped with a suspension system to offload the Lunokhod's weight. At the plant's test station, the chassis underwent electrical tests on a rotating stand with a load mechanism. Deployment of ramps was checked in the assembly shop, and disembarkation of the Lunokhod from the carrier stage, KT module, via ramps was rehearsed. The lunar rover Lunokhod was secured to the carrier stage, KT module, with 4 explosive bolts. Upon activation, the Lunokhod was released, while 2 pyromechanisms simultaneously disconnected the electrical connectors between the Lunokhod and the carrier stage, KT module. Tests confirmed reliable disembarkation. both on evenly deployed ramps and ramps set at various angles. Near Simferopol, Crimea, a dedicated lunodrome was constructed at the NIP-10 Scientific Measurement Facility. For driver training, a lightweight version of the Lunokhod was built using standard systems. Control on the Lunodrome was carried out via cable connection. The Ground Control Center, PUL, housed remote control equipment. The control crew consisted of 3 personnel, a commander, an operator for the Lunokhod's high-gain antenna, and a driver. Initial training involved simple driving tasks, movement across flat terrain, turning, ascending, and descending slopes. As skills improved, the tasks became more complex. The most challenging aspect was driver training, as the human driver became part of a closed-loop control system using telemetry for the first time. Operating the Lunokhod was a task never previously encountered by humans. All contingencies had to be eliminated, and were. Automatic safety systems stopped the Lunokhod if it encountered dangerously steep slopes or excessive tilt. Testing at the control station revealed high physical and psychological demands on the human body. Continuous medical monitoring tracked physiological parameters of the crew throughout training. A major experimental program was completed. Final assembly of the flight hardware was underway. After assembly, the carrier stage, KT module, and Lunokhod underwent autonomous and integrated electrical tests at the control test station. The lunar rover Lunokhod was then docked with the carrier stage, KT module. Using a gimbal rig, the E-8 complex was rotated to a horizontal position. A fit check of the payload fairing followed. Finally, a last round of factory checks was conducted, including a control weighing. Ground control systems and measurement stations were prepared. The flight was planned as follows. After launch, the carrier rocket ascended vertically for 25 seconds to an altitude of about 500 meters, then transitioned to a programmed trajectory. At 125 seconds, the first stage engines shut down and stage separation occurred. The second stage engine ignited. At the 202nd of flight, at an altitude of 80 kilometers, the payload fairing was jettisoned. The rocket continued gaining speed. The control system maintained the desired pitch angle and stabilized the vehicle's orientation. At 375 seconds and a velocity of 4.5 kilometers per second, the second stage engine shut down and separated. The third stage engine ignited, continuing acceleration. At 588 seconds, the third stage shut down and separated from the upper stage. Further acceleration was provided by the correction and braking stage, D module. At this point, the trajectory passed over Transbaikalia and northern Manchuria at an altitude of 200 kilometers. At 958 seconds and a velocity of about 7.8 kilometers per second, the correction and braking stage, D module, engine is turned off, initiating Earth orbit insertion. At the 35th minute of the flight, the landing gear deployed. During orbit, the control system stabilized the craft and performed pitch maneuvers using 8 liquid propellant thrusters. At 66 minutes post-launch, the D module with object E-8 took a second launch position. The correction and braking stage, D module, engine was reignited, initiating departure from Earth orbit. After 400 seconds, delivering a velocity increment of 3,170 meters per second, the engine shut down. 12 seconds later, the D module separated. Antennas deployed. Now, the E-8 spacecraft continued its journey to the Moon independently. Two mid-course corrections were performed based on radio measurements to ensure arrival at the precise time and location for lunar braking. The first braking maneuver placed the spacecraft into a circular lunar orbit. Orbital parameters were measured via radio tracking, and 2 further corrections were made. One to lower the pericenter above the selected landing site, and another to adjust the orbital plane. The second braking burn eliminated orbital velocity is to correct the plane of the object's approach to the landing point. The orbital velocity of the object is dampened. It turns its engine towards the Moon. The spacecraft oriented its engine toward the Moon. A Doppler velocity meter activated, and the spacecraft began free fall under lunar gravity. Velocity was reduced through pulsed firing of the braking engine, followed by activation of the low-thrust engine. At an altitude of 2 to 3 meters, the Kvant 2 gamma altimeter signaled engine shutdown. The Lunokhod-0 spacecraft made a soft landing on the moon. After transmitting images of the landing site to Earth, a command was issued to deploy the ramps. The Lunokhod detached from the carrier stage, KT module, and descended onto the lunar surface. Its solar panel opened, and the battery charging process began. Once charged, the Lunokhod began its scientific and technical mission. This included testing of the mobile platform systems and lunar studies using the onboard patrol dosimeter, X-ray emission spectrometer, X-ray telescope, and soil gauge. Before lunar nightfall, the solar panel was closed. All systems were shut down except for the thermal control system, which maintained internal compartment temperatures no lower than 0 degrees Celsius. The film presents the development and operation of the first phase E-8 complex. On February 19, 1969, at 9 hours 48 minutes and 48 seconds, a launch failure caused by the payload fairing failure prevented the planned mission from being completed. Following investigation, design modifications were made and new E-8 units were prepared to resume flight testing.